professor in civil and environmental engineering here at Nanyang Technological University. So I run the Nanyang Environment and Water Research Institute, along with a lot of my great colleagues here at NTU. At the same time, I'm also editor-in-chief of the American Chemical Society's new journal, Environmental Science and Technology Water. So for those of you on the call, we'd love to see your innovations published in our journal. If there's any way I can help do that, please reach out to me directly. So I thought I'd just say a few words. I actually first came to Singapore in 2008. I had received this interesting invitation to attend a meeting I'd never heard of before, the Singapore International Water Week, along with a Water Leaders Summit. And I was excited. I had to even get on Google and figure out where Singapore was. I had never been here before. And that meeting really changed my life. I've been in Singapore every single year since 2008, and now a permanent resident of Singapore and living my daily life here. So that meeting was a real catalyst, as I said. And I think the meeting we're about to have today will also be another driver in looking at how we take this research, myself as an academic and leading a larger group of academics, how do we get these great ideas and work with our agencies like PUB, along with our commercial partners, those SMEs and multinationals, to try to co-create and develop better technologies, proficient technologies that result in a more secure water supply, not only for Singapore, but for our region. And while I'm on the topic of Singapore International Water Week, I, again, similar to Michael, hope that we see many of you back for that exciting meeting. I'm greatly honored that I'm hosting a roundtable for several of the Lee Kuan Yew Prize laureates. So I'm a bit nervous about that, but I think it'll be exciting to hear from the top leaders in the world in one forum, and we'll be obviously doing virtually. So for me, again, I came back in 2008, and then I actually worked at NUS. I was a visiting professor at the National University of Singapore for about 6.5 years, and I had the most amazing time working with the team at NERI over at NUS. And obviously across the entire country, we have many different groups doing absolutely state-of-the-art work. So as Michael also said, I'm happy to see a diverse group from across the country coming together with our partners and colleagues around the world from various companies and institutions. So it's kind of fresh on my mind today thinking about what's going on in Singapore. Earlier today, I did an interview with Channel News Asia, or CNA, a TV interview, where we were talking about ocean desalination. And one of the questions that was asked is, as we think about Singapore, what are the challenges we have? We have a lot of rain. On average, maybe 234 centimeters per year. It's more than enough water, of course. But not when we think about the urbanization and the land density and the limited catchments. But I think a lot of countries, a lot of regions can learn from Singapore and looking at how Singapore was able to engineer more catchments, to be able to build something like the new Keppel Marine East dual mode desalination facility, a very innovative facility that can treat both ocean seawater as well as freshwater from our expanded catchments via the Marina Barrage. But I think we can, as the group here on the call can think even more about our region. Some people don't realize that Southeast Asia actually is 650 million people. And a large percent of the people in our own region lack access to safe, reliable drinking water and adequate sanitation. So as we think about the great technology developments we'll hear about today from the various speakers, I challenge all of you to not only think of the commercialization and the successes it can bring, but how do we get this very best available technology into the hands of the people who need it the most, those people who are suffering, even with the effects of climate change, that once prosperous or natural plenishment from rainwater may be not enough at times, and at other times, tremendous flooding. So, of course, in summary, we know that Singapore has done well to foster the growth and development of numerous leading edge research groups, along with attracting SMEs and multinational companies and entrepreneurs of all types, including investment, as Michael said, that work in these different domains within the water segment. So here at NURI, I feel very fortunate to be the executive director. We have a team of more than 300 faculty, staff, and students that all work towards a common goal of sustainability. But as a professor, as a lecturer, our main goal seems to be making sure our students graduate, get jobs in the future, and we publish our work in great journals like ES&T Water. But of course, when we were able to secure the funding from our government, different entities, and partner with our companies, what goes beyond that recognition of publications and showing what we've been able to come up with is the more daunting task of scaling it up. What we've developed in the laboratory, we may be able to do some absolutely amazing science and engineering. But when we go to deploy this, it becomes much more challenging. That's where I think we can learn a lot from each other in partnering with agencies like PUB and other government entities, as well as the various companies from small to multinational. So again, I'm appreciative to have this few minutes of your time to say a few words about what we're up to and kind of my vision for the future. But again, I ask all of you, as you're hearing about these new developments, membranes or oxidation, to work with us. Even in NURI, we have a philanthropic division, and our challenge is really to see how can we get this high technology into the hands of those people who need it the most. As one example from today's CNA interview, inorganic membranes. PUB has the largest inorganic ceramic membrane filtration plant in the entire world. And now NURI is building a small one in the rural mountainous region of Thailand, the hill tribe people who are suffering with insecure and not very high quality water. So again, thank all of you for giving me a few minutes of your time to listen in, and I'll be enjoying the rest of the presentations myself. And if you have any interest in hearing more about NURI, certainly drop me an email, give me a call, and look forward to seeing everyone in person when we get a little further along in this terrible pandemic. So thank you.
Thank you very much, Shane. Now, some of you may know the Singapore water story, where the water demand in Singapore is predicted to double by the year 2060, largely driven by demand from the non-domestic sector. The strategy by PUB would be to significantly dial up 2 out of the 4 national caps, namely new water and desalination, to meet Singapore's future water demand. Hence, today's lineup will in some shape or form showcase attempts to move the needle in these 2 areas and more in the effort to secure a crucial national need for our future generations. Our first presentation will touch upon increasing the recovery in the new water production process via advanced membrane systems, which will be presented by Associate Professor Chong or Ziggy from NTU. He is also the Deputy Director of the Singapore Membrane Technology Center at NURI. Ziggy, please.
Hi, Joanne, thank you. First of all, thank you to the organizer for this opportunity to share the advanced membrane technology for high water recovery reclamation developed at the Singapore Membrane Technology Center at NURI and TU. Next slide, please. Next slide. So we know that current Nf-Mbr plus the RO for water reclamation is often limited to 75% recovery due to the poor effluent quality from the Mbr as RO feed that causes the membrane fouling of RO. So here we are taking the advantage of high rejection properties of the nanofiltration membrane, for example, in terms of calcium, magnesium, and organic removals. So the proposed Nf-Mbr will produce a good effluent quality as RO to allow high recovery of more than 90%. So previous work limited by the low permeability of the NF membrane. Here, in this work, we use a novel low pressure nanofiltration developed by the SMTC by Professor Wang Rong for the Mbr application. So this NF membrane is made by layer polyelectrolyte deposition on the UF substrate. So it changes the molecular weight cutoff from about 50,000 Dalton to 200 to 300 Dalton, and having the calcium and magnesium rejection of about 90%. Very important, this NF membrane does not reject the monovalent ions. Thus, it can be operated at low pressure of about 2 bar. So this membrane has a hollow fiber configuration and is operated inside out configuration. This NF membrane was originally developed for hardness removal. Here, we demonstrate that it can also be applied for wastewater application. Next slide, please. So there are two parts in this work. The first part is actually in laboratory scale studies where we optimize the Nf-Mbr. We improve the NF membrane and module for the wastewater applications, assess the overall fouling reductions of the system, and perform some technical economic analysis. In part 2, which is in the current stage that we are in, we demonstrate this technology where we scale up the NF membrane as well as to demonstrate the Nf-Mbr at pilot scale. So we have done a lot of optimization work. So below are the optimized conditions of the Nf-Mbr. So as mentioned, the membrane is a inside-out configuration. It's used in external mode because we still need to apply a low pressure of about 1 to 2 bar for the operation. And this hollow fiber membrane has the internal diameter of 0.9 millimeters and external diameter of 1.4 millimeters. This has been optimized to minimize the clogging of the hollow fiber when operated with the wastewater. And the flux is set at 10 LMH. The filtration mode that we use is intermittent operation with 9-minute filtration and 1-minute backwash, and two-phase flow is applied. In the bioreactor, we actually use a biofilm carrier such that it produces a very low MLSS of less than 1.5 grams per liter. The HRT is set at about 6.25 hours and SRT is 30 days. The feed water is the municipal wastewater collected from a domestic treatment plant in Singapore. So this Nf-Mbr, of course, experienced the accumulation of salt, such as calcium and magnesium. However, it did not impact the biodegradation efficiency, which it has more than 90% of the organic compounds. And also, we check the activity of the biomass, so it does not impact the operation of the bioreactors. So next slide, we take a look at the previous slide. Okay, thank you. So in figure A, it shows the permeate quality of Nf-Mbr versus the UF-Mbr. The permeate of Nf-Mbr has superior quality in terms of the DOC removal. It consistently shows a concentration of less than 2 milligrams per liter. Also, it has lower proteins and polysaccharides content. So when this NF permeate is used for the RO in the RO process, it shows that it can achieve recovery of greater than 90%, as shown in figure B. If compared to a conventional UF-Mbr permeate, it can only achieve 75% recovery. Take note that there's no chemical such as chloramines or antiscalant that has been added to the RO feed. So the reason why it can achieve a low fouling in the RO process is because of the removal of organic compounds, such that there's no synergistic effect of organic calcium fouling in the RO. In addition, as shown in table C, the Nf-Mbr show excellent removal of micropollutants such as the pharmaceutical active compounds, steroid hormones, and PFAS. So the Nf-Mbr can be potentially applied to treat emerging contaminants in the wastewater. Next slide, please. So as mentioned, we're currently in the stage 2 where we actually scale up this pilot Nf-Mbr for 5 meter cube per day system. So in the pilot system, we actually scale up the Nf membrane to 4-inch module. So as you can see in the table, we are still able to maintain close to about 90% rejections of calcium and magnesium, where it's using the pure salt solutions to characterize this membrane. Okay. So similarly, for the pilot Nf-Mbr, we try to use about 6.3 hours HRT, SRT of 30 days. So next slide, please. So this is showing the permeate quality of the pilot Nf-Mbr. As you can see that it can achieve a good removal of the COD, where it's consistently below 5 milligrams per liter. So we are still in the stage to actually take this permeate of the Nf-Mbr and run it through the RO. Next slide, please. So as you can see, the performance of the pilot Nf-Mbr, we did not observe significant drop in the permeability. The fouling of the Nf membrane is observed through the channel pressure drop along the module. This is probably due to the clogging of the fibers. So at this stage, we are still optimizing the Nf-Mbr to obtain a better performance in terms of the N and P removal, as well as to control the membrane fouling. Next slide, please. Yeah. So based on preliminary studies using the lab data, we have compared what is the energy consumption of this Nf-Mbr plus RO at 90% water recovery. As shown, the energy consumption that is used is comparable to the conventional UF-Mbr plus RO at 75% recovery. Take note that the conventional UF-Mbr plus RO cannot achieve the 90% recovery that we desire. So in here, the higher energy is due to the RO is because when we want to achieve the higher recovery, the osmotic pressure is higher. So therefore, it's known that you need to apply more energy in the RO stage to achieve higher recovery. So this is the preliminary data that we have, and further verification using the pilot data is required. Next slide, please. So in summary, the Nf-Mbr achieved a high organic removal than conventional UF-Mbr. Thus, it allows the RO to be operated at recovery of greater than 90% recovery. So Nf-Mbr plus RO is a feasible option for high recovery water reclamation. So other potential applications, apart from water reclamation, we can use the Nf-Mbr for industrial water recycling. And in particular, it has a significant improvement of micropollutants removal. So benefits that you can get, of course, is high water recovery, lower chemical usage, and less energy consumption associated with the RO membrane fouling. Okay. And also it can increase the membrane lifespan. So next slide. So this comes to the end of my presentation. So I would like to acknowledge the NRF for its support in this project, as well as the collaborators, START and JFE Engineering. So if you are interested in this technology, you are welcome to contact me and also leave your questions in the chat room today. Thank you very much, Joanne.
Thank you, Ziggy. I was just about to mention, any questions, please post it to Ziggy in the chat. Our next presentation will focus on the development of high-yield membranes for desalination, presented by Prof. Neil Chong from NUS, where he is a long-standing stalwart in the membrane arena, as well as the Provost's chair at NUS. Prof. Chong, please.
Okay. Next slide. Okay, we thanks PUB for funding this project. In this project, we are working on molecular design of thin-film nanocomposite membrane for brackish water and seawater desalination. As you know, thin-film composite is dominant in RO membrane. And they have some advantage, but also some disadvantage. One of them is the permeability is a little bit low. In addition, the chlorine resistance is not high. Therefore, we try to, next slide, we try to work on two areas to improve the permeability and chlorine resistance. The first approach is to add amino functional UIO6 particle. And why we choose this particle? Because this particle has a wide pore size, about 5.1. It allows water to pass through and reject sodium chloride. In addition, it is hydrophilic, and it is very good stability in water. So the figure show you the particle we synthesize. It has about 100 nanometer. Then we spray the particle first, okay, in the polysulfone substrate. Then we do thin-film polymerization, okay. Next slide. And the top left-hand figure show the PWP as a function of the spray time duration. Okay, the first one is control, then 1 minute, 3 minutes, 5 minutes. Okay, so you can see when you increase the spraying time, the flux increase, the PWP increase. And for 3 minutes spray, the PWP increase 50%. And the rejection for sodium chloride stays the same. And the right-hand figure, at the 50 bar, the PWP also increase, but the rejection drops slightly. The bottom figure show you a comparison between these two membranes. Okay, one is a control, one is the best thin-film nanocomposite membrane. And you can see our membrane has a higher flux and in addition, higher rejection, okay? And this is very impressive, okay? And why they have a good rejection? Because we put sodium, the UIO particle, it has the right pore size. In addition, when you add this particle inside, it has a good compatibility with the polyamide layer. And as a result, the flux increase and rejection also increase. Next slide. And we also study the chlorine resistance between the traditional TFC membrane and our newly developed membrane. And we immerse these two membranes in sodium hypochlorite solution as a function of from 5,000 to 20,000 ppm. And you can see the sodium chloride rejection at 20 bar. When they immerse at 5,000 ppm sodium hypochlorite, no change in the rejection, but it starts to show up at 10,000 ppm, then shows severely difference at 20,000 ppm sodium hypochlorite. The conventional TFC membrane dropped to 82% rejection, and the rejection of the TFC membrane, TFM membrane, is still 93%. So clearly, the addition of the UIO 66 improved the membrane chlorine resistance. And why? There are two reasons. The first reason, because the particle, UIO particle, rejects sodium chloride. In addition, it changes the chemistry. The active chlorine will attack the N- group, N- bond between the UIO and the TMC, rather than the amide bond between the MPD and TMC. As a result, the membrane shows higher chlorine resistance. And this slide shows you another approach. We put CQD, the carbon quantum dots, in the TFC layer. And why we choose this one? Because the CQD, carbon quantum dots, has a very small particle, less than 10 nanometer, and it is easy to synthesize. In addition, it has a tunable hydrophilicity and surface chemistry. And the middle of this curve shows you how do we synthesize. We can use citric acid and put in the oven at 180 degrees, and you get CQD. After that, you can neutralize by sodium hydroxide and become sodium modified CQD. Then we put this one in the thin film composite membrane, the interfacial polymerization. And you can see the PW as a function of these three materials. One is control, no CQD. The middle one is neutral CQD. Another one is sodium content CQD. And the PWP of the last one is high, 4.27 compared to 2.93. Okay, in addition, the rejection are almost the same, 98.7 and 98.6. Okay, so clearly the sodium CQD has a good performance. Okay, next slide. In addition, we try to increase the amino functional group in the CQD. How do we do? When we prepare the CQD, we add ethanol and amine, EA, in the citric acid. As a result, the N component increase. And when the N component increase, it has a better interaction. So the bottom figure show you the PWP as a function of difference CQD with the difference amino amine group. And the one with the 0.1 ratio has the highest PWP, 5.5, compared to the control, 3.87. The rejection drops slightly from 98.6 to 98%. Next slide. Then we prepare this membrane, hollow fiber membrane. And after we prepare the membrane, we also immerse in the hypochlorite solution at a different pH, a different concentration, 2,000, 4,000, 8,000. Then the hypochlorite will attack the membrane, increase the flux. And you can see the flux increase from about 525 to about 10, okay, about 90 or 100%, 90% increase in the flux after immerse at 4,000 hypochlorite, okay? If you immerse too much, yes, the flux increase, but the selectivity rejection reduce. In the case of the 4,000 ppm one, the rejection stay quite good, 98.9%, okay? So this is a way we develop new way to make a nanofiltration membrane. Okay, next slide. Okay, so we try to compare the state of art and brackish-water RO membrane. Okay, the way we do is first we prepare CQD and the sodium or amino functional CQD put in the TFC layer. Then we treat with sodium hypochlorite and increase the flux. And you can see our membrane has a good rejection and higher flux. Compared to literatures, our flux, the red one, we have 10.13, the pure water permeability. And in the case of 2,000 ppm sodium chloride, we have 8.66. They are much better than most people publish, even including aquaporin, they already published. In terms of rejection, we are also as good as theirs. Okay, so we are in the stage to looking for partner to commercialize this membrane. Okay, one of them is start already show their interest, and we welcome you to join us. I think I finished my presentation. We thank PUB and start. Thank you.
Thank you very much, Prof. Chong. Again, if you have any questions regarding his enhanced DFN membranes, please leave that in the chat section. Our next presenter will offer an alternative proposition to reduce the energy penalty of desalination. I am pleased to introduce Associate Professor Yang Hui Ying from SUTD to share her novel concept of coupling desalination with energy storage. Prof. Yang, please.
Yeah, thank you for the kind introduction. Good afternoon, everyone. I'm Hui Ying from Singapore University of Technology and Design. I would like to thank the PUB to organize this great event, and thank for the funding agency, NRF and PUB for the kind support for my research. And I also want to, thank the Singapore Membrane Consortium, for letting me participate in the event. My research is a little bit different from membrane technology. My research is on low energy water desalination and purification technologies. So next page, please. So as we all know, as Prof. Chong and then Prof. Aziz just present, there is an impending water crisis globally. So because of the water pollution, global warming, and then conflict, and then wars between different countries, there are increasing demand for clean water, fresh water, or desalinated water, and there are increasing population, and that make the importance even more significant for getting the fresh water and to support enough support all populations globally. Next page, please. Currently, there are many methods to do desalination, and desalination has been recognized as a #1 solution to tackle the challenge with increasing demand and then decreasing supply for fresh water. So the main technology, as Prof. Chong presented just now, is membrane technology, and that has been generated over at least more than 100 years, and many populations have been benefited by the membrane technology. There are reverse osmosis membrane, and then forward osmosis membrane as well. And then associated with the membrane technology, there are electrodialysis solution, nano filtration, and so on and so forth. So recently, people also utilize graphene as a new material to treat the water. And the second group of technology people utilize to treat water is thermal technology. So there are a multi-stage flash distillations, vapor compressions, multi-effect distillations, and so on and so forth. And then there are a group of in NUS, they are also trying to utilize thermal to generate the dew liquid from the desert area or very dry area, and that is a new direction for thermal-based generation of water as well. And then there are other group of technology. I call them alternative technology. So thus occupy maybe a very small factor of desalination technology currently, but I believe there are a lot of space for such technology. So the alternative technology we're talking about, including the microbial desalination technology. In NUS, there are a few groups are working on that direction. And capacitive deionization, my group actually working on capacitive deionization for more than 10, 12 years. And then we have invented a different stage of capacitive deionization technologies, and then also ion concentration polarization. That part I can also summarize them as alternative solutions for desalinations. So membrane, especially RO technology, relatively more expensive than most of the other technologies, but then it's the most effective one currently. And most of the membrane and thermal method need additional facility. For example, the thermal technology, at least you need to have the huge heater that support the water being distilled and then come back to the stage that we can utilize them in our daily life. Energy consumption for both membrane and thermal process as high as more than 3K watt-hour per meter cube, and that is the current situations. Capacitive deionization is one of the major sort of like alternative solutions that humans utilize in our daily life. So basically you have two plates, one for positive and one for negative. So when the seawater come in, the negatively charged particles will go to positive charge the plate, and then positive charge the particle will go to negative charge the plate, and that is as simple as the high school student can analyze, can understand, and that is the basic for capacitive deionizations. But then there are a few, for example, like advantage and then also disadvantage for capacitive deionization. So the main like advantage is a very small value of direct voltage or current need to be utilized in the electrode, very small, because above 1.4 watt, the water is going to be generated into hydrogen and oxygen. So any anything you want to apply in water in terms of voltage must be below 1.4 watts. So that there is only a small amount of energy is required for CDI. And then oppositely charged ions will be absorbed in different electrodes. Positive one attract negative, negative one attract positive, and that is the basic. However, when you have this kind of system, attract opposite charged ions, you can immediately imagine that when the surface being covered by one kind of charge, for example, the negative plate covered by positive charge, when you have sufficient positive charge to cover the entire surface, you stop. And that is the limitation for the capacity. And the electrons are regeneratively because, when you short circuit, those electrons, when they lose the attraction force from the plate, they will go back to water, and that is the regeneration process. So next page, please. And then by having this kind of a CDI study on the CDI for 5-6 years, my group start to realize there are a new group of material can be utilized in this kind of mechanism, but generate a totally different effect. And that group of material is battery material. So we are going to introduce the revolutionized idea basically to utilize battery material in the desalination process. And I'm going to introduce some basic concept over here. So we want to realize one very interesting phenomenon. We want to have ion selectivity that doesn't exist in any of the previous methods I introduced, either membrane or thermal method. So when you have thermal, you have heat to generate the water vapor, and there is no difference for positive charge or negative charge ions, sodium chloride, in the solution. And then for membrane, you just remove all the particle in one shot. There is no difference for positive ions and negative ions. But the battery material, the battery electrode material, basically there are one group of material, one big group of material. They can be utilized in water-based solutions, and they are targeting on different ions only. For example, for the anode material, once they are targeting as sodium, they will only targeting as sodium. Even though sodium is positive, magnesium is also positive, but they will ignore the magnesium ions, only taking the sodium ions. And that is very, very unique in all of the ion, sort of the water desalination technologies. Basically, we are dealing with ions with selectivity instead of remove them in one shot. Next page, please. So the desalination battery is one invention that when we utilize the battery type material in the electrode. And then I'm proud to say that in Singapore, we are the first group of working on this area. And then globally, we are also pioneer in this research. So this desalination battery combine the desalination and the energy storage together. Next page, please. And then we can increase the capacity significantly by, previously when we are talking about, purely CDI system, we can only remove 70 or 20 milligram per gram, based on the electrode weight. But then with this, new battery-based material, we can increase by 1 order of magnitude the capacity. And then we have enabled ion selectivity that doesn't exist in any of the water treatment technologies. Next page, please. Okay, so we basically utilize the desalination battery with high capacity, low energy cost, and then we also enable the system to have energy harvesting effect, because we only taking in sodium ions, and then when we release the sodium ions, we generate a current flow, and that will being a sodium ion battery directly. Next page, please. And then in the future, we have a few targets in our future research project. The first one, we want to enable the energy efficient desalinators with high salty level. Next page, please. And then we want to have the extremely high accurate ion selectivity. Next page, please. And then we also want to have high energy generation and recovery. Next page, please. So in the future, we want to create a sustainable, low-cost solution on the precise control of ions in the energy storage and then desalination systems. I'm sorry, I think my slides is a little bit long, but I want to thank POB and NRF for the funding support, and thank you for your attention today. Thank you.
Thank you very much, Prof. Yang. Again, before we move on, just a reminder, please post your questions in the chat and select everyone. We receive some that's going to the host, and sometimes that it will drop out and we will miss capturing it. So again, if you have any questions, make sure you are posting it towards everyone in the section. Now, the next topic on system to forecast algal blooms might seem disparate from the earlier presentations. But if you can recall what the source input for desalination is, seawater, then this topic is critical to mitigate the risk of fatal membrane fouling in our desalination plants. I'm pleased to introduce Associate Professor Vladan Babovic from NUS to share on this system that leverages machine learning. Prof. Babovic, please.
Thank you, Joanne. Thank you very much. Thank you, POB, for organizing this. Very interesting, insightful session. Yes, I am going to talk about something a little bit different than membranes and water treatment, but this is nevertheless very relevant. Maybe next slide. Some of us who live in Singapore for some time may remember fish kill occurrences. The latest, largest one that occurred recently is happened in 2015, so 5-6 years ago, where in a space of 2 days we lost more than 600 tons of fish. This is simply due to the harmful algal blooms which occurred in our marine environment, microorganisms, so the phytoplankton that occurred. The bloom itself essentially suffocates the fish. It enters in a gills, and fish can stop breathing, and that's it. So the question really goes, and now you put it in the context of food supply and a big initiative that we have here, 30 by 30. We should be self-reliant on more locally produced food, 30% by the year 2030. Obviously, aquaculture becomes a very interesting source, but the aquaculture is exposed to these sort of phenomena. It's very, very tricky. So what we sort of tried to do in this research, in this project, was to analyze the origins of this in order to produce early systems that may advise the fish farms. The problem is, however, that some of the runoff is not under the national control here in Singapore, and I'm also showing here some of the press snippets of water samples, about water samples from Johor River. So very high concentrations, chemical waste even leading into marine environment, particularly in Johor Straits. So the question really goes, what can be done about this? So maybe we can move to the next slide. Yes. So we did, of course, quite an extensive data science exercise and combined both the data that were collected in the field. This is sometimes a prohibitively expensive exercise because you have to send vessels. Vessels need to take samples. Then these samples need to be brought back, analyzed in the lab. So your frequency of visit is not very high. You're taking spot samples and so forth and so forth. So in order to supplement this, we have also introduced what we call surrogate data, or highly reliable computer model, a highly reliable computer model that would sort of interpolate the data in space and in time. So first step that you do, of course, is you carry out correlation analysis and see how the nitrogen, phosphorus, so PO4, suspended solids, total oxygen correlate with chlorophyll A, dinoflagellates, etc., sort of leading to total percentage of phytoplankton. But that is only a part of the story, and this is sort of, it does not give you causality. It gives you correlational strength between these signals, but it doesn't give you a cause of where, when the bloom will be, or particularly the forecast when the bloom will happen. So we moved to a machine learning to help us in this. Maybe next slide. So we took two different approaches, and I do apologize for all of you who are familiar with machine learning that I'm introducing this in such a way, but maybe it will be helpful for some others. We use something called supervised learning. And in supervised learning, you need to show examples of input and outputs. So in our context of algal bloom, this would mean that we would have to have samples of many algal blooms to actually say, hey, these are the intensities, etc., which is difficult. But how does supervised learning works is that here's an example of vending machines. And how does the vending machine knows if the coin you insert is 10 cents or 1 cent or 5 cents or 25 cents? It should be very sturdy environment. So what if I provide lots of examples, lots of coins in a vending machine? What the machine learning algorithm needs to do is just needs to learn this separation lines that separate different classes of coins. And on the next slide, please. Yes, I'm showing an example of unsupervised learning. What does unsupervised learning? It says, hey, you know what? I really don't know what these samples are all about. But perhaps these machine learning algorithm can help me establish different classes. So here, I'm looking at the same example of the coins that I have just used. And it seems like I can clearly see here 3, but possibly even 4 distinct classes. So this is what unsupervised learning does for us. It sort of reorganizes things for us. It helps us. Dissect similarities between the objects that are being classified, right? So maybe next slide now. So what we did, we looked at our algal bloom data that were collected between 2014 and 2016 to see what unsupervised algorithms would tell us. And what is very interesting is that unsupervised algorithm managed to distinguish among different classes, and I will explain these classes a little bit later, but they would give you an events that offer a different abundance for different phytoplankton genus, corresponding to this what is known as self-organizing feature map, which is a machine learning technique. But then when you do this in the first step, maybe next slide, then you start asking yourself, how does this translate to risks? And you can see, okay, maybe there's a low risk condition, relatively a high condition, etc. So we started digging deeper into these clusters that have been identified by self-organizing maps, by our unsupervised machine learning algorithm, and then trying to interpret the events by what they are characterized. So next slide, please. Then you use this, since you know that in each class you have no risk, low risk, medium, etc., you ask yourself, can I now show this to another kind of machine learning algorithm? In this case, it's supervised, because I know what these classes are: low, medium, high risk, etc. And we use the two techniques. One is called CART, a decision tree CART, and the other one is called random forest, to actually learn the sort of thresholds which determine a different kind of behavior in the environment. So in this case, this is a CART decision tree. You can see that various clusters have been identified, and these thresholds are also identified. Maybe next slide. So what does this really mean? This means that decision and the clustering, so unsupervised clustering and decision tree together, they actually lead to advice and establishment of a progressive monitoring program. This is in a way a progressive warning system from low risk to high risk of algal blooms, and these is then coupled to trigger a different form of surveillance and monitoring and decisions, right? So if you remember at the very introduction, I mentioned that we have imperfect knowledge about what happens in Singapore, what happens in Malaysia, which factory may release something. So actually we are relying on parameters which are relatively easy to monitor, but that would trigger to higher a different kind of models that would perform computation analysis at a higher fidelity. Next slide, please. So the integrated operational response system to bloom warning, it really uses a different clusters, different classes to lead. So if you're in orange cluster, you say, hey, you know what, you should go for spot sampling, fly drones, and go for high fidelity algorithms. But if you are in a green cluster, low risk, no action is needed. So actually this whole stuff becomes very much an informed decision making. This is my last slide. Thank you for your patience. Joanne, thank you. I hope I'm not too much over my time.
Perfect. Thank you so much, Prof. Babovic. So our earlier presentations by Prof. Chong, Prof. Chung, Prof. Yang, and Prof. Babovic showcase the latest research in the water sector, which is the genesis of future technological applications and solutions. Now, our next segment will address the gap that exists between research and commercialization, driven by one of our National Translation Centers on Separation Technologies, the START Center. Presenting on low energy reinforced flat sheet membranes is Ms. Goh Lee Mei, the engineering manager at START, an industry veteran and among the very few flat sheet specialists in Singapore. Lee Mei, please. Lee Mei, are you on mute, perhaps?
Hi.
Yes, can hear you now.
Yeah. Right. Thanks, Joanne, and very good afternoon to all of you listening in. Today I'll be sharing an innovation at START, which happens during an effort to scale up to translate a patent from SMTC, the Singapore Membrane Technology Center. This This technology is about the fabrication of reinforced membrane on the industrial size casting line and its application in pressure-driven membrane processes. All right. As many of you would have known that in pressure-driven membrane processes, there is an increasing demand for higher flux, and because this will lead to lower energy consumption. And there are actually many ways this can be achieved. For example, you can increase the amount of active membrane that can be packed inside a fixed volume of spiral wound module. The other way is to optimize the chemical formulation. And another way is to optimize the spiral wound module. So the reason why we are looking into this innovation is we believe that the reinforced membrane is one of the means to achieve this goal of improving the flux of pressure-driven membrane processes. Okay, a little bit of background. Sorry, can you move back? Yeah, a little bit of background on why we get started on this project. Back in 2018, START has this task to evaluate a couple of patents from NTU, which were about to lapse, and this patent for SMTC was identified as a potential to commercialize, to scale up. So this technology is about casting a lab scale fabrication of reinforced membrane, particularly for the PRO, pressure retarded osmosis application. So it's about casting the polymer dope directly onto the mesh instead of the polyester backing. The reason this was done was because this will reduce the concentration polarization, which is critical for PRO applications. So we took this technology and we attempt to scale it up on the industrial size casting line. And we encounter a couple of difficulties. The first is that we are unable to coat a 1 meter cross width without defect, without leak. And the other difficulty is that because of the structure of the mesh, which is very different from the polyester backing, there's significant creasing on the pilot line. Fortunately, an idea from the team, the invention team, enabled us to cast this reinforced membrane on the industrial size casting line, and also with optimization on the tension, we successfully scale it up. And because of this, we actually changed the process of casting the polymer dope, and this enabled us to file a new patent, which was filed in end of 2020, which now not only covers PRO but all other pressure-driven membrane processes. So the neat thing about this, the reinforced membrane, the new process, is that we are able to coat the polymer onto the mesh, which in our case is a permeate carrier, halfway through such that it doesn't coat completely, so that we have the permeate channels on the back side of the membrane, as well as the active layer on the front side of the membrane, meaning that we can actually combine the permeate carrier and the membrane into a single leaf. Okay, as in conventional spiral membrane, there are three layers leaf set, but now we can have a 2 layers leaf set. Okay, this will enable us to reduce the leaf set thickness, as well as cost reduction, and also higher productivity, because we will be working with less leaf in each leaf set. We believe and have ideas that this, the reinforced membrane, will be able to let us reduce the flux and achieve the goal of a next generation spiral module. Next slide. Okay, this is a visual representation of the industrial size row of reinforced membrane. If you look on the right side, it's a 1 meter width reinforced membrane, and it's more than 50 meter length. On the middle, you can see the back side of the membrane. The side shows the mesh, which is the permeate carrier, sorry. And then the polymer is coated halfway through such that you still have the channels on the back of the membrane. And the front side is a smooth membrane, which acts as the active layer. Next. Right, so a quick timeline on what happens in 2018. We attempt to scale up the reinforced membrane. Overcoming the difficulty, we're able to coat the reinforced membrane on the industrial size casting line with a new process. And then we are able to roll it into the spiral wound element. And end of 2020, we filed a patent on the new process. And for all types of pressure-driven membrane processes. In terms of result, we have validated the coupons to withstand up to 35 bar for seawater desalination. We also validated the performance at brackish water condition, which has more than 99% rejection. And the spiral wound, validated the spiral wound for up to 15 bar. Next slide, please. So in terms of applications, we believe and have ideas that this reinforced membrane has a lot of potential for pressure-driven applications in all pressure-driven applications in UF, MF, NF, RO, FO, PRO, as well as membrane distillation. And we believe that this will be the path to the next generation spiral wound module. And currently there is a non-exclusive licensing and spin-off by Namiton Private Limited, which is the subsidiary of City Synergy. So with this, I want to thank our funding agency, ADB, NTU, and our collaborators and advisors from SMCC, NERI, NTU. Thank you.
Thank you very much, Li Mei. Now, also from the Start Center, I'm pleased to introduce Mr. Stevie E, project leader and a water industry professional, leading the low-pressure nanofiltration technology translation from lab scale to commercial scale. Stevie, please.
Hi, good afternoon, everyone. I'm Stevie from Start Center, that in charge for the low-pressure nanofiltration membranes. Today, I'm going to present to your showcase technology translation for lab scale to a commercial scale for a novel low-pressure nanofiltration membrane. Next. Before we move further, just to know, I'd like you all know briefly the idea of this low-pressure nanofiltration membrane being invented is because of that the existing conventional water softening method, be it ion exchange, zeolite, or lime soda treatment system, it is either producing a large amount of sludge to be handled, or it requires a larger footprint. And the conventional nanofiltration membranes actually require high energy consumptions, since it requires to operate at 5 bar above, depends on the feedwater TDS. Next. So this low pressure nanofiltration membrane actually is invented by Professor Wang Rong and Dr. Liu Zhang from SMPC. And the key feature for this membrane is that it's able to operate at feed pressure of 2 bar or less, and is served mainly on the water softening purposes. And for this technology translations, we are facing different 3 main challenges, whereby the first one will be definitely the cost-effective raw material. The second one is the chemistry and process review throughout the upscaling from a small size into a bigger size. And then it's the module design that we need to face. We also face some challenges on that. And our current status is that we successfully fabricate the substrates manufacturing from 1.5 kg up to 20 kg batches. And then we have did the module validations for NF membranes from 2-inch diameter, 3-inch, 4-inch, and up to 8-inch commercial size diameter for the NF module. And we do have a different MSc work as our industrial partner for this particular project. Next. For this, the technology translation, mainly we are talking about the manufacturing feasibilities. For these NF membranes, we have to tackle 4 main approach, which firstly we have to optimize the substrate fabrications. Thereafter, then we have to move into the optimization on the selective layer formation, which is in this case we are using layer by layer process. After that, we move to module fabrications from different sizes, from smaller 2-inch up to 8-inch diameter, and then eventually we will need to perform a different kind of test at the modular level to see the consistency of the product. So like I mentioned before, the challenges that we face, first thing is to replicate and repeat the substrate parameters where we get the data from the lab research and compare it to the current pilot setup in our start center. And secondly is to maintain similar performance by switching from a laboratory grades of chemicals into industrial grade chemicals. This is not only to make sure the compatibility from the lab grades to industrial grade chemicals, we will see a huge cost saving in terms of future manufacturing mass capacity. For our current status, the substrate fabrication process has been scaled up in the start center from 1.5 kg batch up to 20 kg, I mentioned before. And then we have a module fabrications that have been scaled up from 2-inch diameter up to 8-inch commercial size. And our layer by layer process has been optimized for different modular size. Next. So like I mentioned before, changing on the raw material selection. If you look at this slide, the photo on the left hand side is the cross-sectional substrate, hollow fiber substrate photo that is produced by pure analytical grade chemicals, and the right hand side is the cross-sectional hollow fibers that using industrial grade chemicals. What we can see in terms of the internal diameter and outer diameters, it is quite close to each other, and we have successfully did the process validations using cheaper industrial grade chemicals, which eventually will give us a lower cost at manufacturing scale. And the substrate characteristic successfully been replicated, which close to the high purity analytical grades chemicals. Next. So by comparing to the physical properties on the IDOD may not be enough to justify the performance. So we need to proceed to test on the substrates, comparing the industrial chemicals and the lab grade chemicals. So the test conditions, we set it at 2 bar and we test it with 2 different kind of solution. First thing is the PWP, which is pure water permeation. We are using deionized water. And second test, which refer to SWP, is the salt water permeation, where in this case we are feeding it 1000 ppm of magnesium sulfate solutions at 2 bar feed pressure. So if you're looking at the light green bar compared to the light blue, what we can see is that industrial grade chemicals show comparable performance on permeability and in fact comparable performance on the divalent ions rejection as well. And these successful applications suggest that the manufacturing on large scale is feasible. Next. So optimization on the substrate size and the staining. Next, we have to move into other process of optimizations. I mentioned changing from the lab scale to industrial grades not only save us from the cost, and also it gives us the availability of the chemicals for industrial grades whenever we need it. And of course, this chemical has to be compatible to meet the LPNF performance. So next, the next challenge will be on the semi-dynamic methods, which we do some modifications as on the process. If you look at the photo on the top left, three top left, whereby we are using vacuum assisted method to lift the chemicals into the hollow fibrous membrane to form the coating. But this method is only applicable for smaller diameters module. But when we apply this method for 4-inch diameter or even 8-inch diameter, it doesn't work. So we have to modify the system become from vacuum assisted into a pressure driven by maintaining a certain pressure and velocity to make sure the coating in the substrate is evenly distributed. Next. Having the layer by layer process be optimized, then we have to move into module fabrication and testing. So if you look into the photo, we are purposely using the material of a clear PVC pipe, or in fact a white PVC. These are the commercially available module housings, which has a benchmark against a commercial product, which is a existing UF membrane what they are using. And we perform different longer term tests is to confirm that the stability and repeatability of the substrate and the LBL process that we have performed. Okay, coming to the test result, if you look into this diagram, we actually we have plotted out the different sizes, module dimension of the NF module that we have been fabricated in start center, from glass tube, 2-inch diameter, 3-inch diameter, 4-inch diameter. We have producing two different lengths, 0.5 meter and 1 meter length, and the largest that we have produced so far in start center is an 8-inch by half a meter length NF module. So this diagram, we have tested it with two types of solution: deionized water for pure water permeation and 1000 ppm solution for divalent rejection test. So what we can see is that across the smaller size glass tube up 8-inch diameter, we're able to achieve from the top left, the diagram, pure water permeability. Even at the 8-inch diameter, we're able to achieve 12.1 mmH per bar of the water permeability. And if you look at the lower left of the diagrams on the divalent ion rejections, from a glass tube size up to 8-inch diameter, we are achieving more than 80% divalent rejections. And even at 8-inch diameter, we have achieved the 11.6 mmH per bar, the permeability. So the optimized formulations, spinning process, and our modified LBL process, we're able to achieve the project target of more than 10 mmH per bar permeability and more than 80% rejection. Next. So just a quick one. So other than testing the different modular size at the lower concentration water, we also repeat the test using a 3000 ppm mixed salts and 5000 ppm mixed salts to see how it works at the 2 bar feed pressures being applied. So for this 3000 ppm mixed salt solution, it consists of a magnesium sulfate, calcium chloride, and sodium chloride, which is a mixture of a mono and sodium ions. And then it consists of about 1800 ppm total hardness as calcium carbonates. And for the 5000 ppm mixed salt solution, similarly, they do consist magnesium sulfate, calcium chloride, and sodium chloride. But in this case, it consists of slightly lower total hardness, which is 1600 ppm, but it consists of a slightly higher sulfate content, which is 800 ppm. And again, what we can see across 2-inch diameter of the NF module that we produce, up to 8-inch, we're still able to achieve, even at 5000 ppm mixed salt solution, 2 bar feed pressure, we are able to achieve 80% total hardness reduction, and at the permeability of 8.1 mmH per bar. Next. So for a longer term test that we have did on the NF membrane, similarly, we apply 2 bar at the 5000 ppm mixed salt solutions, and over these 100 hours of the test, what we observe is that the permeate flux, what we're able to achieve is about 7.1 mmH per bar across these 100 hours, and the total rejection what can achieve is on average of close to 82%. So if you look at this at the first few hours, there's a slight dip on the performance. That is due to 1 and 2 fiber breakage, which after we rectify it, it goes back to normal thereafter. Next. So the summary is that the membrane process has been scaled up and validated at modular level. The key membrane fabrication process, which in this case LBL, can be easily automated for cost-effective manufacturing. Our next step, perhaps we can do more pilot testing at different kind of water, and then we are in fact ready for commercializations. The potential area for this application will be on the municipal water softening, RO pre-treatment, replacement of home RO, and food and beverage wastewater treatment, in particularly for COD removal. Next, I'd like to thank our funding agency, EDB and NTU, our inventors and collaborators, Professor Wang Rong from SMTC, and our staff team. Thank you. Thanks.
Thank you very much, Stevie.
Thanks.
So next, another successful translation project by START is on membrane distillation, a low-cost alternative to conventional distillation or evaporation processes. This will be presented by Dr. Sebastian Hernandez, project leader at START. Sebastian has extensive membrane experience both in academia and industry, in Colombia, the US, Australia, and now Singapore. Sebastian, please.
Good afternoon to everybody. Well, I'm going to present today the Tribor hollow fiber membranes for membrane distillation. This is a project that is being here in the start from some years, and the inventor from this is the Neil Chong from the Department of Chemical and Biomolecular Engineering from NUS. I just want to start with the problem statement. Majority of the industries will generate a lot of wastewater with high salinity. Not only the salt, the RO, the seawater has high salinity, but also other industries like, for example, electronics or other industries in water purification. Most conventional physicochemical biological treatments don't remove this salinity. So, however, there is some technologies that we have seen here in these presentations that you can work with it, but reverse osmosis is a good tech for this. It's limited because the salt concentration depends on the osmotic strength, and we have other technologies like the evaporation that we saw before that we need a thermal very increase in energy, not only in the thermal, not only with RO with its pressure, but also thermal energy for evaporation. So the idea is that we can use inexpensive technologies that have zero liquid discharge and are critical for brine treatment and minimize this environmental impact. Next, please. So, like I said, the inventor is Professor Neil Chong, and the idea is that we have hollow fibers that instead of one channel through this fiber, it has 3 channels. It's a 3-bar hollow fiber membrane. This gives us a high surface area. It's about 30 to 40% increase in area that increase the contact between the salty water through the membrane, and you can have better, more flow of the water, of the vapor through the membrane to produce pure water. So it's a reduced footprint because you can, with higher membrane area, you can have less membranes in the plant. We can have, from this invention, it has higher vapor flux. It produces between 8 and 10 LMH per bar, compared to 4 to 6 LMH for the single bore, and it has a higher efficiency. Also, given the structural, the geometrical structural part of this membrane, the idea is that the membrane has a very structural stability. It can containerize, it could be reduce the footprint, like I said, and it's important because the footprint will be lower. And this will improve the ease of troubleshooting. The challenges, of course, is the suitable chemistry and process, because you have to change a little bit of the chemistry of the materials, of the compositions to get a suitable membrane that has 3 pores, and the fabrication tools that gives you the right shape of this membrane. And the module design will go through the same as the single pore membranes, but like I said, it will increase the area. Next, please. So in the current status, we are in the phase 3. We are going from 1.5 kilograms to 25 kilograms batches, and we are programming now to 50 kilograms batches. The production is successful up to now. We are doing the pilot fabrication in process, and most of this evaluation of the performance is doing an EWTCUI. There is a collaborator from the Nyan Polytechnic, and we are doing also a pilot scale evaluation with an industry partner with this MEMSIT innovations. At this moment, we are producing 2-inch and 4-inch modules, which it will give us a better performance, and we can test it in the field. And also, these modules are working with vacuum membrane distillation, which is with one of the sides of the membrane is in vacuum, which promotes the evaporation of the water of the other side, and only the water vapor will go through this through the one side, and it will be filtered to the other side. So the idea of this is that we already validated the vacuum membrane distillation. We treat other systems, but this is the one that really worked. And as you can see here in the figures, we went from the laboratory scale mold at the 1.5 inch around to a commercial scale of 4.4 inches. Next, please. So you can see here between the membrane made in the lab, correct, to the pilot scale, like you see, there is some differences in the membrane structure, but we can have salt rejection with this membrane that produced here at start, a rejection of around 99.8%. And with using a 3.5% concentration of salt. And the permeability is really good because it goes around from 9 to 10.9 LMH per bar, which is in the range of what we wanted. So if you can see the comparison between the specification at the lab, at the validation at start, we are getting around the same geometry of the membrane, the 2 millimeter diameter around. The inner diameter is a little bit smaller, but it's around what we wanted to be in the range. And the good thing about this membrane that we are producing here is that it's more strong than the one is produced in the lab. As you can see, the flux is around the same of the vapor, and the liquid entry pressure, where the membrane gets wet, is higher than the lab produced. Next, please. So with this, we get to an agreement between STAT and MEMSIFT Innovation to do the pilot scale evaluation of these membrane distillation membranes. And the idea is to get to the performance of these tri-bore membranes against the commercially available membrane. That will be the next step. Of course, the idea is to get to a pilot site and get into the site to do with real water. And the idea is to get to a 2-year project or be in a 2-year project with a specific aim of semiconductor wastewater. Like I said, not only seawater, but we can work with this electronic water, other waters to work with this membrane technology. Next, please. Well, like a summary and acknowledgement, well, we can fabricate this tri-bore membrane in a scale, an industrial scale, and it's a feasibility manufacturing. Like we demonstrate, we are now in between 2-inch and 4-inch module performances. We are producing these modules here and testing it in-house and with our collaborators. The pilot system is about 5,000 liters per day with our industry collaboration. And of course, we really appreciate the collaboration between the academia and NUS, EWTCUI, and the industry partners in MEMSIFT. So I want to thank everybody at START and our projects and our collaborators here. Thanks.
Thank you, Sebastian. Now we've heard 3 great examples from on scale-up and translation projects. So if you have any questions, post them in the chat and we'll make sure to get back to you on that. Our next speaker hails from industry, where his company, H2MO, successfully developed bioprogrammable membranes for commercial applications. I'm pleased to invite Mr. Ong Zi Guan, founder of H2MO, to share on this membrane technology, which includes new water and desalinations as its target applications. Mr. Ong, please. Mr. Ong, maybe you are on mute. Would you like to check to unmute?
Yes, hi, good afternoon, ladies and gentlemen. Hi, I'm Ong Zi Guan, founder of H2MO. We are a Singapore company in the forefront of membrane innovation. We work with SMTC of Newly, Professor Wang Rong, and we're focused on using new biomaterial membranes for liquid separation process applications. In Singapore, obviously, the main application would be in the area of water purification or water recycling. I'm currently in China, so my signal may not be great. but I am honored to be given this opportunity to share with you our RO membranes made from our proprietary bioprogrammable membrane technology. Next, please. Today, two of the greatest global challenges facing the 21st century involves providing sustainable supply of clean water and energy to highly interrelated resources at affordable cost. Membrane technology is expected to continue to dominate the water purification and water recycling technology sphere. I paraphrase phrase from Shriya Dev, a founder of Bioseparation. Membrane liquid separation processes are so common that in industrial settings, it uses as much energy as all the US cars and trucks combined. Okay, but however, there are problems associated with existing liquid separation membranes, including limited permeability, excessive energy consumption, higher membrane systems costs, and maintenance issues due to membrane being prone to various types of fouling. Therefore, to overcome this global issue of clean water and energy, problems associated with existing membranes must be solved. Next, please. Okay, to this goal, H2MO's partner, Professor Wang Rong from SMTC of Newry, NTU, started research 10 years ago into biomimetics, which is the innovative design concept that draws inspiration from nature and its elements and processes to solve our membrane problems. We look to cell membranes for inspiration. The work involved overcoming numerous challenges over the years, such as finding the right formulation of biomaterials, the stability of the biomaterials, incorporation of biomaterials onto a substrate layer characteristics, membrane module production issues, and more. The road was long and arduous. In 1918, there was a breakthrough and success in producing the biomimetic membranes, aquaporin-free. We were able to make membranes with different membrane characteristics and functions using different biomaterial formulations. These functional properties include reverse osmosis, nanofiltration, forward osmosis, and membranes with specific ion selections. We call this technology bioprogrammable membrane, or BPM for short. We are currently in the process of commercializing a BPM with support of SMTC of Newry, and we intend to roll out other BPM membrane types for different applications over time. We now have a demo RO system operating at PUB's new water plant and at our own facilities. Our BPM RO membrane has proven to be stable and reliable, achieving a steady 2 to 3 times higher water permeability compared to existing RO membranes. They have equally good and stable salt rejection, realized 2 to 3 times lower operating pressure, 2 to 3 times lower pumping energy consumption, lower investment costs due to BPM RO systems being low pressure systems as opposed to high pressure systems or conventional RO systems. And finally, lower operating costs due to energy savings as well as potential savings in membranes because of the better anti-fouling characteristics of our RO membranes. Next, please. Another key characteristic of our BPM RO membranes is that it is configured as a hollow fiber, as opposed to the conventional spiral configuration of most RO membranes. Our hollow fiber RO membranes offer better packing density, better physical flow and pressure characteristics. These characteristics, coupled with a far lower operating pressure of our membranes, result in better anti-fouling abilities, leading to better performance stability and lower maintenance. The BPM RO is a first in hollow fiber RO for brackish water treatment. From our demo BPM RO plant at the Singapore New Water Plant for the recycling of treated wastewater effluent, we have measured a lower energy consumption of 0.2 kilowatt hour per cubic meter, and this is about a 50% savings in pumping energy compared to existing RO membranes on site. Next, please. Yeah, our BPM membranes are therefore ideal in a wide range of liquid separation applications, such as potable water purification, ultra pure water purification, point of use purification, wastewater treatment, wastewater recycling, new water, zero discharge applications, seawater desalination, groundwater remediation, and concentration. Next, please. H2MO is committed to providing this groundbreaking technology to the benefit of the world. Its team, with over 16 years of experience in membrane manufacturing, is currently in the process of setting up our membrane manufacturing facilities in China. Our China facility will manufacture BPMR modules, manufacture BPMR liquid separation systems, and undertake further R&D into the new application for BPMR membranes, as well as developing novel manufacturing processes with the aim of achieving full automation of our production line. H2MO is looking for partnerships in marketing channels and partners to participate in the co-financing of the rollout of this world-changing technology. Yeah. We'd like to thank everyone for this opportunity to speak today, and also to SMTC of Newry for being our partner in this project. Thank you very much.
Thank you, Mr. Ong. Now, our final speaker of the day is Mr. Christopher Gasson, the owner of Global Water Intelligence, GWI, which is a preeminent source of information on the global water industry. Christopher is an authority on water finance and markets. He is also the driving force behind renowned events, including the Global Water Summit, the American Water Summit, and the Produced Water Society seminars. Besides his involvement in GWI, he is the co-founder of the Global Water Leaders Group and leading utilities of the World Network. We are pleased to have him here today to wrap up this event with his insights on the future of water and the latest industry trends. Christopher, please. Christopher, I think you're on mute. Perfect.
Hi. So I thought I'd talk through some of the sort of things which are driving sort of technology innovation, globally in the water industry at the moment. I've sort of pulled out 5, I think, and then I was going to sort of look at, some of the most successful startup technologies that are around at the moment. So first of all, can you move to the next slide? Here we are. I mean, this emerging contaminants thing has become a sort of huge deal in the US, largely because of the sort of, frankly, quite crazy regulatory limits they've imposed on PFAS in the US. I mean, there's a part of the reason for that is this Mark Ruffalo movie, which I've got a little picture from there. All the cows died, and the chap goes off and sort of sues everyone to get the money back because the cows have had too much PFAS. Anyway, the big problem with PFAS is, well, first of all, getting an economic technology to remove it. And I think that, some of the technologies we've heard from this morning, such as the Nf-Mbr and indeed the low pressure nanofiltration would be quite appropriate for that. The big challenge, though, is this disposal route issue. What do you do with the as a residue? You end up with sort of residual PFAS waste, and at the moment they have in the past been disposed on land, and they can't anymore. And so that's a big challenge. Next slide, please. In Europe, the main sort of issue is these other sort of emerging contaminants, pharmaceutical products, pesticides, endocrine disruptors, and we're seeing stricter regulations being sort of pushed out in Switzerland, the Netherlands, Scandinavia, and at the state level in Germany. And again, it's created an opportunity both for membranes and other sort of alternative absorbents to deal with this. Can we move to the next slide? Then, this whole sort of value from waste proposition has been quite a big deal in the water industry. I suppose there are 3 different angles that people are looking at this from. There's the sort of energy side. And I think just sort of comparing, the value of sewage to other sort of biological waste streams, it's sort of there. And I think one needs to keep that a little bit in context. We're not necessarily going to be able to sort of completely change the world with anaerobic digestion of sludge and wastewater, but it is a huge opportunity nevertheless. There's the sort of thing on the right there. We've got talking about bioplastics. Essentially the ones which can, the idea of bioplastics is that they are biodegradable, and they're also, sourced from sewage sludge. And I think that, again, we need to put this in a bit of context. At the moment, this market share of the kind of bioplastics that one can be manufacturing is this sort of 1.2% of PHA, biodegradable plastic. So again, it's a relatively limited opportunity at the moment, but it could be something that dramatically changes as people look to eliminate non-biodegradable plastics from the supply chain. And it is a very complex process at the moment. I won't go into it, but that's the main reason why it's expensive. It's been used, or at least they've piloted it in Legoland, it's not Legoland, it's the town which town wastewater treatment plant which supplies Legoland, where they try to make Lego bricks from the sewage from the town, but they decided that it wasn't actually economic for them. And then we have this sort of mineral thing. That is a picture of the Enviro-Water Minerals plant in San Antonio in Texas, which unfortunately failed this year. It was essentially sold off for a fraction of its cost because it was not actually able to separate the minerals from the brackish water brine that the desal plant was pulling out. And that was really, I think, more of a commercial failure than a technological failure, in that they, I think, didn't have enough redundancy in the system, and as a result, it just couldn't. There were so many different things that could go wrong that it never sort of performed to standard. But it's been bought by a company which want to use the plant for taking lithium out of the groundwater and other sort of brines with lithium in them. And that's sort of quite interesting to watch. And again, I think that capacitive deionization technology we saw with the selective separation, I think that's a very interesting technology from that perspective. Next slide, please. Hydrogen. I mean, this is a thing which has sort of crept onto the sort of water agenda in a bit of a roundabout way, in that I think there's a sort of growing sort of feeling, I don't know whether you call it a sort of consensus yet, that hydrogen might be the solution for energy storage, and if we can't build batteries which are sort of good enough, why not store energy in hydrogen and move around it as hydrogen. And there are a number of different sort of opportunities here. There's the fact that the fuel cell technology and electrodialysis technologies, basically the same membranes. And you can see BWT, which is a sort of Austrian water treatment company, has basically sort of bet the farm on these electrodialysis membranes being applied to hydrogen fuel cells, and they've sponsored this pink hydrogen fuel cell racing team to do that. I mean, other sort of hydrogen opportunities that people are looking at are the fact that hydrogen You know, it literally means water carrier. It needs water. You know, doing these, you know, co-locating hydrogen production with water utilities makes some sense. I think we're seeing a bit of action on that in Australia. I'll look at that at the next slide. Also, you know, if you're going to be producing hydrogen, you need pretty clean water, and you know, some of these sort of processes that one for water treatment might be adjusted to create the sort of create hydrogen or take part in the whole process. So that's one of the reasons why hydrogen has become a bit more exciting. Just the next slide, please. You can see here some of the sort of hydrogen sort of ideas and pilots and what have you that are being sort of undertaken around the world. You know, it's still very much a sort of a cottage industry, but yeah, we're certainly seeing some sort of interesting hydrogen-based programs. And I don't know, I think I'm looking to the sort of NEOM project in Saudi Arabia, and there's a wastewater project in Australia, which is going to you know, really be show the way for water. Can we have the next slide, please? So I mean, the whole sort of digital thing, I mean, that is you know, that's one of these things which is you know, it's a bit of a catch-all. In fact, I've been told by my colleagues that they're not allowed to talk about digital anymore because it's almost impossible to find somebody who's trying to do anything in water which doesn't have a digital angle. You know, it's become totally ubiquitous. But looking at the sort of different angles that have been sort of driving the sort of growth of digital and actually making money for it, and I think non-revenue water has been a big area for that. Combined sewer overflow, you know, that's a huge area of spending in the US, you know, I mean, I guess that, you know, in some way it also connects up with the what we saw about the red tides in Singapore, and how to, you know, measure and monitor those things and, you know, come up with better ways of dealing with it. You know, COVID monitoring has sort of opened up a huge new angle on the sort of the whole you know, analytics side, and you know, I think that is going to be something that gets built into wastewater treatment plants globally in future. That kind of public health role is now embedded in the utility sector. I think just a sort of remark here, I mean, it's the most sort of crazy price we've ever seen paid for a water company was the sale of Innovise, which is a company which started out doing hydrological modeling. You know, it has, you know, it sold for basically 10 times revenues, which is extraordinary. And, you know, I guess that just shows how much people expect of the digital sort of thing in the water sector. Can we move to the next slide? So just this sort of desal sort of overview. I'm just thinking, I mean, I have to say, listening to the presentation this morning, I was just completely bowled over. I mean, I felt that the, you know, Singapore sort of, you know, investment in, you know, water technologies has, you know, I haven't really seen the sort of the dividend. I mean, I seem to remember, you know, I've you know, been to, I suppose it was the first Singapore, you know, the precursor to Singapore Water Week in 2005 with the IDA World Congress there, and you know, one felt that Singapore had decided that it had spent an awful lot of money on sort of upgrading its water resources system, and it was determined to get a sort of technology dividend from that, that it was actually going to be able to create an export industry you know, based on the amount it was spending on water. And, you know, it's only really now that one can see, you know, I suppose it's sort of 16 years later, one can see that this dividend is real. You know, the amount of money that you people have been spending, and the time and the concentration and the people that you've brought together and so forth, I think is really actually going to, you know, it's beginning to change the world. And, you know, I felt these little charts here sort of a little bit irrelevant compared to, you know, because each of one of these technologies that you've presented, I think moves the story along, you know, in quite an important way. Just sort of overviewing what is sort of going on in the world. I think, you know, just looking at the chart on the right there, we were suggesting that sort of microbial desalination is actually on the way out, but today we've got a report in Water Desalination Report about how you know, there's a pilot in Spain which is actually really quite serious on the microbial desal. I mean, it was one of these things which was a very faddish technology thing sort of 5 years ago, and we didn't really see any results, but I think this shows that that's come along. Forward osmosis, I think, is still a sort of market exit thing. I mean, all of the companies which were involved in that, like sort of Oasis and Modern Water and so forth, have gone sort of backwards rather than forwards. And chemical saturation, I mean, that turned out to be, you know, it's an interesting technology. You can sort of throw handful of magic fairy dust into seawater and all the salt precipitates out. That's great, but the amount of trouble you have to sort of re-separate your fairy dust and use it again just makes it completely impossible as a technology. I mean, I don't know what else to say. I mean, there we got the sort of capacitive deionization, which we heard a bit about. You know, these aquapur and things, they're sort of moving upwards, but still we're not really seeing the commercial competitiveness for seawater. It's mainly a brackish water thing at the moment. So a lot of this sort of counter-current high recovery RO, that seems to be one of the things that's getting attention at the moment. Looking at this slide here, the left-hand side, I think it's interesting. You know, graphene has still been a little bit more disappointing than one would like it to have been. Again, it's turned out to be, you know, the salt rejection rate's really too low for it to be used for seawater. And you know, if you're in the brackish water business, you know, there's you know, the value is just not there in the membranes. I mean, you know, it's brackish water desal membranes are not competitive on performance in the same way that seawater membranes are competitive on performance. So, I mean, you know, looking at, I mean, obviously, you know, you've got to start somewhere, and brackish is the place to start. But you know, the sort of volume value sort of equation has to be sorted out a bit. This barrel technology from Veolia is very interesting. That's sort of putting all the membranes in one huge membrane vessel with these little smart connectors which measure the conductivity of the water in and out of the membranes, and they can sort of switch some of the membranes on and off if they stop performing and so forth. I think that's going to be make a big change. I mean, these things here, I mean, printed membrane spacers, I mean, that's quite similar to some of the ideas that you people have been developing. I think that's going to, again, be, you know, quite important. And what else have we got? You know, this machine learning software. And I mean, you know, I think that the point about the algal bloom forecasting, I think that is really the next step here. I mean, talking to Aqua Power about this, you know, they see that being able to, you know, measure biological activity in the seawater and then adjust the way that they run the desal plant, as you know, in real time as they get feedback from whatever's going on in the sea, as the future of managing biofouling. And I think that, you know, again, some of these technologies that we're seeing from Singapore are going to be quite important for that. Disk tube reverse osmosis, that's a thing usually used for sort of leachate treatment. And this sort of, again, closed circuit RO, that's Desalination stuff. This is this high recovery thing, which has become very important in the industrial market. I mean, if you looking at the way that the world seems to be going on the seawater market, I'd say that data is becoming the main technological driver and incremental improvement in membrane performance. In the brackish market, the main driver has been the requirement for higher recovery rates by industrial customers, going up to sort of 90% with a lower energy consumption is, that's been the big focus of technology. So finally, just looking at who are the, can we move to the next slide? Who are our unicorns? A unicorn's supposed to be a startup with a value of $1 billion, and the best we've got in the water industry is 100 million, and I would say Gradient is raising money at the moment. That will be there. Source Water, MI Systems, Voltaire, capacitive deionization, again, another thing which is interesting in Singapore, and Kakadu, network data management. So that's my view. I think that that's all I would have time for. So thank you very much. It's been a great morning for me and afternoon for you.
Thank you very much, Christopher, for sharing your top 5 and also just, very thoughtful and very candid analysis of all of that. We are actually right on the dot, okay, slightly over. Just a quick sharing on SIW 2021. This year, the Singapore International Water Week is a fully virtual event held over 12 days from the 21st of June to 2nd of July. This virtual event will feature close to 100 keynotes, thematic webinars, workshops and solutions spanning the urban water cycle, as well as a virtual expo featuring some 100 exhibitors with the latest cutting-edge solutions and technologies. So do join us at SIWW 2021 online, and we look forward to seeing you there again. Lastly, do participate in the post-event survey that will pop up as you exit the screen. We very much appreciate your feedback on how we can serve you better. On behalf of the organizers, I would like to extend a big thank you to all 9 presenters and to all of you who joined us today. We had nearly 190 attendees at peak, so thank you for spending your time. As mentioned at the start, we will take up the questions posted offline and share those as well as the presentation slides today with all the attendees. Do give us some time to collate this before we send them out. Have a wonderful rest of the day. Stay safe and healthy. Thank you, everyone.